this video lecture, we are going to see about the theorem of three-moment equation to solve indeterminate beams, or otherwise called as Clapeyrons theorem. So this topic is included in unit 1 of structural analysis. So this method is used to analyze indeterminate beams which is having consecutive spans and supports. So the Clapeyron theorem of three moments describes the link between the bending moments at three successive supports of a horizontal beam in civil engineering and structural engineering. So you consider a beam with three supports, successive supports. So here it is a simply supported condition. So moment at A equal to 0, moment at C equal to 0. We already know that simply supported condition, the bending moment is 0. Simply supported at the C point is bending moment 0. But here at B, even though it is simply supported condition, there will be some moment towards B to A and there will be some moment towards B to C. If you sum up the moment MBA and MBC, then only it will become 0. It is a simply supported condition, so the bending moment at the simply supported condition should be equal to 0. But even after the summation of MBA plus MBC. But at A and C, there is no span on the left side of A and there is no span on the right side of C. Hence, the simply supported condition in the moment is 0 at A and C. So here it states that three successive supports of a horizontal beam. So three successive supports of the horizontal beam, we can be able to find the moment. So we already can declare MA0, ME0 and we can find MB from this methodology. So it is one of the analysis method for indeterminate analysis. It is very easy to calculate also. So this is applicable to any two adjoining spans of a continuous beam and can be repeatedly used for other two adjoining spans. So you can even increase the number of spans left and right, and we can extend the equation or extend the solution procedure to the nearby spans successively. For n number of spans, we can able to write n minus 1 simultaneous equations. It gives the solution of redundant moments at the supports along with the conditions of statics. How it can be understood? You have to write an equation comprising of MA, MB and MC. If it is further support of D, you consider these two spans. You can able to write the equation by considering MB, MC, MD. And also you imagine another support here, that is A dash. You can able to write by considering these two spans with MA dash, MA and MB. So initially you solve for ABC spans, and if it is a purely a simply supported condition, it can be neglected, and which is 0, MC is also 0. You can directly get the value of B. If it is continued to the left side span and right side span, then the indeterminacy of the beam is increased. For example, this is the number of span considered. What is the I value here? I is U minus E, number of unknowns minus number of equations. What are the unknowns here? So we are dealing with the static indeterminacy. Static indeterminacy. We are not dealing with the kinematic indeterminacy. we are dealing with static indeterminacy. So number of unknowns are RA, RB, RC, RD and RE. RA, RB, RC, RD, RE. So totally 5 number of unknowns. Normally we have 2 number of equations for beam, because if there is no load of inclination, all the loads in the beams are generally perpendicular. So we can neglect summation of fx 0 equilibrium equation, summation of fx equal to 0. We only consider summation of fy 0 and summation of moment equal to 0. So that's why the equation of equilibrium is considered to be 2. If there is any load of inclined manner, if there is any load which is inclined in its application, then there comes summation of fx0, summation of fy0 and summation of moment equal to 0. Otherwise, you can take the number of available equilibrium equation as 2. So in this case, 5 number of reactions are unknowns, 2 number of equations are available. So totally 3 number of indeterminacies to be solved. For solving any number of unknowns, we need equal number of equilibrium equation to solve a particular problem. Here 3 number of unknowns needs 3 number of equations. 3 number of equations. So by using theorem of 3 moments, first we can write the equation by using this spans RB, RC and RD. RB, RC and RD. And then we can write for this RA, RB, RC, and finally other combination we can write for this RC, RD, RE. And also we can apply the boundary condition. Here it is purely simply supported condition RA and RE. So we can eliminate to 0. So this equation comprising of the unknowns RB, RC and D. We can eliminate any one of the variable and we apply to this equation. Anyhow, we can able to find out the number of unknowns RB, RC, RD. So 3 number of unknowns. So 3 number of equations we can able to write and further we can able to solve. So that's the basic idea. So in our examples, major problems will consider only 2 spans. Very simple problems only given to the students in examination. Anyhow, you have to understand that if it is there is number of spans, you can able to form the equations of n-1 equations and you can easily solve the simultaneous equations. Already you have studied in mathematics how to solve the simultaneous equation. So you can apply that concept to solve the number of unknowns by applying the boundary conditions. So consider 2 adjoining spans of AB, BC of a continuous beam ABC. Span AB, BC are L1 and L2. Moment of inertia is I1 and I2. Because we are going to employ I1 as well as I2 here. So next step. In this figure, it is a bending moment diagram of the span shown in the previous slide. That is A, B, C. So this MA is some fixed moment. Fixed moment we have calculated in the previous video lectures as WL square by 12, WL square by WL by 8 like that. We assume some moment MA is available, some moment MC is available, some moment MB is available. Then the bending moment diagram is like this. So what is this diagram? It is a positive bending moment diagram. I already explained how to draw the bending moment diagram. So you mark the available moment here and you superimpose. If it is a trapezoidal like this, you have to superimpose the free bending moment diagram WL by 4 when it is a simply supported beam with a central point load W. The free bending moment diagram is WL by 4. So you have to superimpose the free bending moment diagram over the moments which we have arrived through any methods. So this is the original bending moment diagram for the given structure. So this is how we have calculated in the problems. So in the same manner, so this free bending moment diagram is always positive. So that's why this diagram is superimposed in the upper side. And this moment will always negative. In major times it will be negative. So it is extended to the downward side. So you are considering MA means it is extended up to this joint C, and MC means from A to C it is extended. So when it is overlapped, here we can have some moment of MB. So this is MB, MA and MC. So we considered, we assumed this type of bending moment diagram for our formulation of equation. And the distance, here it is the span of L1 and L2, and we have to locate the centroid. We have to locate the centroid. This is the centroidal point. So from the left it is x1. If it is the centroidal point here, from right it is x2 for the parabola bending moment, positive bending moment or free bending moment. For this triangle from A to C, for this triangle, the centroid will be here, that is 1/3 of L1, or from here to here it is 2/3 of L1. For the span of L1 it is 1/3 and 2/3. For the span of L2 it is 1/3. This distance will be 1/3, because if it is a triangle, the centroid will be nearer to the area of higher value. Always the centroid will approach towards the higher area of cross section. So generally the centroid will be towards the higher area of cross section. So this area will be higher. So it is 1/3. The remaining will be 2/3. In that aspect, it is mentioned that 1/3 of L2 and 2/3 of L3. 2/3 of L3 for the span 2. So sagging moment is considered positive, hogging moment is considered as negative. So in this A1, A2 be the area of bending moment due to the loads on simply supported span ABC. So we have considered the beam ABC and we draw the area A1 and A2 are the bending moment diagram considered to be a simply supported bending moment diagram. When it is a parabola, for a simply supported condition, the bending moment diagram, when it is a parabola, if a simply supported beam loaded with a UDL of W, then the bending moment will be a parabola. So we have considered a UDL load in a simply supported case for L1 and N2. So x1 and x2 are the centroidal distance from A as well as from C. So in the previous slide we have noted that x1 and x2. It may be noted that for the span AB, BC, B is the intermediate support where A and C are the left and right support respectively with respect to B. So now consider the rotation and deflection diagram. So this is deflection and rotation diagram. If the rotation is like this, the deflection will be towards downward. Here the deflection will be towards upward. Here the rotation is theta B to A. Here the rotation is theta B to C. And this will be in opposite nature, B to A and B to C. So in order to solve the unknowns, we need additional equation. That is what the compatibility equation. Many times I have repeatedly telling that compatibility equation. What is the compatibility equation? If any equations formed with the consult of rotation as well as deflection, that is called a compatibility equation, which is additional equation than the equilibrium equation. What are the equilibrium equations? Summation of fx 0, summation of fy 0 and summation of moment 0. These equations are already well known to us, which are equilibrium equations. But this equation which we formed according to our problem will be the compatibility equations. The slopes at B for the span B2A and BC respectively are same due to the continuity at B. So this will be same. Theta BA and theta BC will be equal depending upon the continuity. So this condition is also known as compatibility condition. So now from this triangle we can able to, so this is our beam. So we have our rotation like this and also the deflection like this. So if you take TAB as the deflection for the span L1, theta equal to opposite by adjacent. Normally theta will be tan theta. We can able to neglect tan theta as theta, which is opposite by adjacent, that is TAB by L1. Similarly, theta BC is TCB by L2. So TAB is the vertical deflection or deviation of A with respect to tangent B, and TCB is the vertical deviation of C with respect to tangent at B. So in many books there are many number of notations for the deflection. Sometimes you use Y, sometimes you use delta. So there is no problem in that. You can familiar with each notations while practicing. TAB and TCB can be obtained by using moment area method. So this is very, very important. In this theorem of three moment, we are going to use moment area method. What is the moment area method? We are going to draw bending moment diagram for a given beam section. We are going to draw some bending moment diagram. We consider the area of bending moment diagram divided by EI. So what is the formula for slope in moment area method? Area of BMD divided by EI. What is the formula for deflection? Delta. So this is the formula, area of BMD into the centroid. X1 is the centroid. So the deflection is equal to summation of area of M by EI diagram between the points into the centroid. So we are going to use the moment area method to determine our deflection. So here you kindly note it down. The deflection is equal to area of bending moment diagram into centroid divided by EI, divided by E. First of all, I am considering TAB, so that is for the span of AB. So I am taking this parabola, which is consisting of the area A1 and centroid X1. So completed. Next one, half BH. So for the span L, for the span L1, it is a triangular type of variation. No, it is a triangular type of variation. So it is half, B is the length, H is the moment, half BH, and from we are going to write TA to B. So from A it is L third, L1 by 3. It is the centroid. Next one, consider this triangle. MB. So half into L1 into MB, that is the area of bending moment diagram, into 2/3 of the remaining distance is 2/3 of L1. So we are going to separate into two bending moment diagrams. So from it is 1/3, next it is 2/3. So similarly you can write this equation TCB for the next span. So here it is A2. So A2 into X2 is the positive bending moment area and centroid. And for the span L2, MC is the vertical height, L2 is the span. So half into B into H into from C it is 1/3. So L2 by 3 plus the middle moment MB is common for both the spans L1 and L2. So MB into half into L2, half BH into 2/3 of L2 by 3, 2/3 of L2 by 3. So you consider this triangle and this triangle. It is 2/3 of L2 by 3. For here you consider this triangle and this triangle separately. You can able to differentiate both the triangles. From here it is L2 by 3. For this triangle it is 2 times of L2 by 3. So we arrived some equation for the deflection. So next theta BA equal to theta BC equal to TAB by L1, which is equal to minus TCB by L2. Why it is minus? If you apply a rotation, here it is theta AB. If it is positive, theta CB is the negative one. So that is why minus TCB by L2. So theta AB by L1, that is already it is EI1 there, and we have included L1 for this term L1, and you have substituted the terms here and you included the minus. Next one, on simplifying, if it is common, that is EI is common, you can neglect this value. So how it can be simplified? You multiply inward. You multiply inward MA L1 square by 6EA L1. So then that is MA into L1 square by 6 EI1 into L1. So it is MA L1 by I1. So you take 6 outside. So that it is multiplied to the other side. So first, for the first step, you bring that A1 X1 to any one of the side, and MA, MB and MC to any one side. So MA L1 square by 6 plus 2 MB L1 square by 6 plus 2 MB L2 square by 6 plus MC L2 square by 6 into if you are multiply L2 inside 6L2 and also 6L2, and I am taking EI as common and cancel EI. I am not going to use EI because I am taking EI is constant. Only I am going to multiply L1 inside. So 6L1, here also 6L1, and I am going to bring that term to the right side. So which is equal to, so A1 X1 is minus A1 X1 by L1. Next one minus A2 X2 by L2. So you take 6 outside and bring to the right side and cancel L1 here. So it will become MA L1 by I1. You cancel only E. So it is I1. Here you put I1 in all the terms, and I2 for this term I2, here also I2, and for this term also I1 and I2. You include I1 and I2. So it remains MA L1 by I1 plus you take 2 MB outside. So and you cancel L1 and L1 square. L1 by I1 plus L2 by I2 plus MC, you cancel L2 by I2, and you take 6 outside, 1 by 6, and multiply to this other side, that is right hand side. So it will become numerator. So minus 6A1 X1 by L1 I1 minus 6A2 by X2 L2 I2. So you will get this equation where I1 equal to I2 equal to I, then you can imagine it's a prismatic beam, and you can even simplify this equation like this. You can cancel all I1, I2 from this term. If it is I1 equal to I2 equal to I. So MAL1 plus 2MB L1 plus L2 plus MC L2 minus 6A1 X1 by L1 minus 6A2 X2 by L2. So this equation is called theorem of three moments, or Clapeyrons equation. From this equation we can apply the boundary conditions, or we can formulate many number of equations for the successive spans. If it is if it is RA, RC and RB, we already know that moment at A equal to 0, moment at C equal to 0. So you can eliminate this term and this term, you directly get MBA value if you know the bending moment area and centroid. So this is the procedure. So procedure how: draw a simple beam moment diagram for each span of the beam, compute the area of above diagrams A1, A2 up to number of areas AN, and locate the centroid of such diagram X1 and X2 up to Xn. It must be remembered that the distances X1, X2 are the centroidal distances measured towards the ends of each span. Identify the support moments which are to be determined, MA, MB and MC. Apply the three moment equation below where the beam is not subjected to support settlement. We derived the equation without support settlement. You have to add this term. When it is a support settlement problem, and you will be given the value of del A, del B. That is, support A sinks by this amount, support B sinks by this amount. So it will be some exceptional problems. You might not given with the such type of problem with the support settlement, even though you have to aware of this equation including the support settlement. Finally, you solve the simultaneous equation, number of simultaneous equations formed by this theorem of three equations, and finally calculate the support moments, and you can further you can draw the bending moment diagram. So this is the procedure, and what about the Clapeyrons three moments equation. So you have to familiar with this method, and you can practice many number of problems. It is very easy to attend in the examination also.